previous video. This is video 3. This will include the end of this problem, and perhaps I have to make a separate video for the set of problems, because I saw that covering all the problems in this video at this moment will take a lot of space of my device, and so it is not possible to upload on YouTube also. So as per the restrictions, I'm just doing this stuff in 4 series of lectures. You can say some lecture is too a heavy word for my age. Anyway, so it will be a 4 series video. This third one will simply show you how to do things using Lagrange, basically how we work with all this. And in this video I thought of adding a very important fact, rather an idea that which might be very much debatable, which is at the end of this video, when I solve the problem, you'll see that you will see that it is very intuitive, or you can say for some it is counterintuitive to say that the result I got is a one-liner from Newtonian Mechanics. So why the hell did I do all of this stuff using all of this complicated mathematics, all of this deeper knowledge? Well, this debatable point will be made clear after the 4th video, where we will get some real hard nuts to crack. They will be really very very hard problems which will shake your Newtonian mechanics, which you think is your savior for the moment. So anyway, that's very debatable. Many physicists debate over the capacity of Newton. Even I debate. He used to do things, and there's an interesting story. It's not a story, it's a fact. It's an established logic that Newton's work was copied from his students, mostly. Like, he figured out what his students were developing, and he was like a political leader of India. Like, he used his power and position to do certain kinds of deeds which are bad. Obviously, there is no doubt that Newton was an absolute genius, but it happens when you get so much power. When you are sitting on a chair called the Lagrangian chairholder of mathematics, when you are the president of the Royal Society, you might become adamant and kind of think yourself as the ruler of Bengal, like that. So then what happens is that you simply misuse your talents. So Newton misused the papers of his students, and you might ask me how I know all of this stuff. 200 years back, I was not there. Well, if you closely read his philosophy and the principles of natural philosophy, some stuff like that, there are clear evidences, and there is in fact a whole lot of books written to show that not all of Newton and Faraday's works were true. These two scientists did not give credit to people on whom they have made their contributions. In fact, they rejected many papers of many of his students, but it turned out that Newton's world is made up of the hard works of many of his students, and they go unmentioned, and they are not credited to the extent they need to be. Like Newton calls, and it is very certain that you cannot have everything in your name, like Newton's law of cooling, Newton's law of heating, Newton's law of motion, Newton's law of this, Newton's law of that, Newton in optics, Newton in thermodynamics. Everywhere there is Newton. Well, you might say that it is very logical for me to say so, but let me tell you that if it is so, then we could not have found any such facts. Even Stephen Hawking said that it is not possible for Newton to do so many things, and there are clear-cut evidences that his work was taken from here and there, and he used his power, pomp and position to outweigh those people who were actually behind the whole of the world of Newtonian mechanics. And let me not say Newtonian mechanics, it is called Newtonian physics. In fact, he was like the king at that time. Not king, I mean king of physics, like that, and things like that. But one thing to admit is that he was really a genius and very clever. In fact, great people are great in every field, be it bad or good. Great people are always great. They are great at doing all types of things. He was great in doing things like inventing calculus, inventing laws of motion. He was also great in rejecting papers and then taking things from there. Anyway, I'm not telling that Newton is a bad scientist or Newton had a bad character. What I'm telling is that every kind of man who is very great, like Rabindranath Tagore, for the fact, they will have two sides, and we are usually not aware of the other side. for that matter, and that is why I am talking about Lagrange, because Lagrange is a much more deeper and fundamental uh, concept than Newton. So let us be back to our problem. Spring has spring constant k, mass is m, the generalized coordinate is Cartesian in nature, it is x, and spring is massless. This is the natural position. I said the kinetic energy was half m x dot squared. Now if you have given a thought to the potential energy, it turns out to be that of the spring. The spring will store the potential energy, right? Half k x square. This is the potential energy. Well, so we have defined L as T minus V. So what is our L from these two? You simply subtract V from T. So you get L as equal to T minus V. Now from Euler-Lagrange you know that d by dt of partial of L with respect to partial of, okay, so there we wrote q dot, here our generalized coordinate is x, so we write x dot, this is equal to partial of L with respect to partial of x. X is our generalized coordinate. There I wrote q because it was a generalization at that point. Now so we will replace L with this. So what are we getting? Love the silence. Yeah, so this is what you are getting. Now how to proceed? Well, you take each term, break it into parts and do the partial. Partial of half m x dot squared with respect to partial of x dot is like you do derivatives. It is that 2 gets cancelled with this half and mx dot. So it is mx dot. Partial of half k x square with respect to partial of x dot. Now answer this question. Is x a function of x dot? No. So can you do the partial derivative of x with respect to x dot? No. So the partial of this term with respect to partial of x dot is 0. This gets ruled out. This is mx dot. What is this? Partial of this term. So is x dot a function of x? No. Can you do the partial? No. This gets ruled out. What you are left with this one. This is minus kx. The partial of this term with respect to del x is minus kx. So what do you get? So you are getting m, sorry, if you remember d by dt, we had a d by dt, right? Now inside you are getting here mx dot, the LHS is equal to, remember in our spring mass system, in this case a very simplified one, no friction was there on the block, so no non-conservative forces acting, so which means our q j is accordingly 0, that capital Qj is 0, source of any dissipation, you know. So here we are getting m minus kx, I guess, yeah, this was the RHS, this is the LHS. So what can we write the LHS as? Okay, this was mx dot, I wrote it wrong, mx dot. Now this dot operation and this d by dt, if you put it, m is constant, so it becomes m x double dot. It is basically d by dt of dx by dt, right? Second order derivative of x with respect to time. This is equal to minus kx. This is the equation of motion of a system. Well, this is very much consistent with Newton's law. What Newton's law says, this is mass times acceleration along x direction is equal to the force due to spring, and which is acting in opposite direction. So this is the equation of motion of our system, and hereby we show you how and illustrate by this simple problem how we will apply Euler-Lagrange to solve mechanical systems. This was very simple. There will be far more complicated systems in the next video, upcoming video, there will be 3 to 4 problems discussed, which will be very big, and so that is why I made this one very short. Now we come back to our topic, that is actually Lagrange or the Lagrangian formalism for the matter useful or advantageous over Newtonian mechanics? Well, everything has its own pros and cons, and as I said that Newton was not 100% perfect. He did things here and there, he did things on his using his own genius. He was really a mighty genius, I accept the fact, and I'm a great admirer of Sir Isaac Newton, but I'm aware of whatever he did. So basically he was a mighty genius with immense power in terms of political influence, and so he used it later, but anyway, that has got nothing to do with science. So we are back to our topic. Well, Newtonian mechanics is very powerful among high schoolers. At the elementary level, it's very useful, very easy to understand. It is not incorrect, it is correct with some boundary conditions. It is applicable, well, our Lagrangian is also applicable with those boundary conditions, and Lagrangian for that matter is not interested in forces acting on a system, it is interested in the energies, and perhaps that is what makes this more simple, far more simple than what you do in the mathematical computations in Newton. And basically Newtonian domain of physics is based on observations, whereas Lagrangian is based on pure mathematical beauty, where you use the theoretical concrete knowledge of physics to do things. And so Lagrange versus Newton will be always Lagrange over Newton, because Lagrange will win the match. It is simply because this makes things simpler, where there are actually some problems where the systems in real world, not only textbookish hypothetical problems, I'm talking about real world problems, where those forces might get a bit messy and doodly to work with. So that kind of computation becomes really a headache for people, and physicists actually need very smart procedures to work with. So by that I mean Lagrangian helps, but for high schoolers we use Newton. Newtonian mechanics is our basics. Before or without knowing that, we should not proceed to Lagrangian, but Lagrangian helps in many cases. There are, as I said in the beginning, in the previous video, that there are some other dynamical systems which will give various complicated forces, and we do not consider those forces at all by using Lagrange, whereas it gives us deeper insights into these things by using Lagrange. So that is the use of Lagrange as such, and it has got other uses in mathematics also, in engineering dynamics also, in various practical fields like mechanical engineering, where engines are used, and various other related concepts. So we are waiting for our problem session to be upcoming video, and that will be the end of this course of Lagrangian mechanics. And this let me tell you something, that this type of video series won't help you to get into Lagrangian at one go. You need to do things, you need to do the problems yourselves, a variety of problems perhaps, but this video will only give you a deeper understanding of the theoretical aspects and the numerical aspects of how we are doing Lagrange, what is happening, what are those things. Thank you. I hope you enjoyed.